Hi everyone, welcome to my channel Pure Biology, and today I come with the second part of the Hardy-Weinberg law. And in the first part I have already explained the Hardy-Weinberg law, and this is the second part. Okay, so what is that? Here this is the derivation of Hardy-Weinberg law. Derivation. So derivation is that Hardy-Weinberg law, this states that population will remain in the equilibrium. The genotypic frequencies always be p square plus 2pq plus q square. Okay, and the addition always equals to 1 or just towards 1. It may be possible. To understand the basis of these frequencies at equilibrium, allele frequencies P and Q square taken, not P and Q square, P square. P square and Q square taken as A and capital A and the small a. Suppose the two alleles in the locus, that is, one is A and capital A, another is the small a. Capital A is the dominant and the small a is the recessive. So here the allelic frequencies will be, one is the p square and another is the small q square, small p square and small q square. And here the p, small p plus small q, that remain 1. Suppose if this is 1, how is that possible? Okay, first I have to check. If this is p square plus 2pq plus q square is 1, that is p plus q whole square equals to 1. So if whole square may be just removed by the process of this, so here the p plus q equals to 1. In that way, p plus q equals to 1 with random mating. So random mating is occurring, that means small p plus small q, that will be 1. And what is the random mating? Here it is meaning that each individual of any population has the equal opportunity to mating with any other individual of that population. This is the random mating. That means any individual can mate with any one. Obviously within the same species, you can say, or within their individuals that remain within the same species. Okay, and the relation between allele frequency Q frequency and the genotype frequency is particularly simple if all gametes are present in an area and the genotype frequency is expected. Okay, here is a mistake that random mating is not that particular species. Obviously any individual is there, but of a population. Okay, not a species. This is mentioned wrong. Of any population, of the one individual of any population that can mate with the individual that remain within this population. Okay. So here, if we think that there are all gametes are present in an area and the random mating is taking place. So what are the expected genotype frequencies, or what will be the expected genotype frequencies? That means suppose PA, small p, it's the A's frequency. So here this will be formed in that way, like that small p, capital A, that means small p square. Okay, small pa, that means small p square. Why this is p square? Because when homozygous condition is there, that means A is not remain only 1. A is remain with 1 capital A. That is 1 capital A with 1 capital A. Here the 2 capital A is multiplied and form the p square. Clear? And another the individual that is formed small qa. Okay, small qa, from this small qa may be produced pq, small pq. That means capital A and the small a. So here the A, that means small p, that's why p small q. From here the two gametes or two individuals may form. One is small pa or small qa. Small pa is formed, that means the frequency may be small p square. If small qa formed, that means frequency may be small pq. Okay, what is saying that? That means PA and PA is multiplied, then form P square, and PA and QA, from here it is formed the small pq. Do you understand? Again I repeat how this is formed. If small PA cross with this small PA, that means the P square, small p square. Or you can say if this only the small p that breed with the small p, then form the p square, small p square, that is the homozygote form, capital A, capital A. Clear? And if this small p that breed with this q, small q, so here form small pq, that is the frequency, that is capital A, small a. Okay, so first you have to have understood that what is the allelic frequency and what is the genotype frequency. This capital A and the small a, these are the alleles, and small p and small q, these are the genotype. Clear? So these are the allelic frequency and these are the genotype frequency. That means allelic frequency form from these and genotype frequency form from small p, small q. Clear? So here if p is multiplied p, that means p square. Okay, a, so here a. Clear? Again small p and small q, so here's p q, that means this, that means this. Clear? So this is the genotype frequency and this is the allelic frequency. Clear? Now the frequency of QA here, if QA is there, the individuals may be formed PQ, Q square. That means they can breed with PA or can breed with QA. How this is possible? Just see, Q into P, then this is PQ, and Q into Q, this is Q square. Clear? Here form this, here form this. That means this is A, this is capital A, this is small a, this is small a. Understood? So these are the form. One is the allelic form, another is the genotypic form. And here another thing is very important, that this graph, if you follow this graph, then you can see that proper allelic frequency or genotypic frequency from one another. That means you cannot identify or you cannot calculate proper genotypic frequency from the allelic frequency. Clear? We can just observe or expectation. It is dependent on each other. That means they are closely related. Like that, if 200 is observed, then expected is like that 196. So they are very close to each other. Not the exact value we have got from this allelic frequency to genotypic frequency or vice versa. Clear? Now this is an example. A is 800, capital A, small A is 185, and small a equals to 15. So how we calculate the small p and the small q? So the process is explained in my previous video. You just check out that one. So here I just put the values. Okay. 2 into 800 plus 185 divided by 2000 equals to the value is 0.8925, and the q value is that 2 into 15 plus 185 by 2000. So answer is 0.1075. Now we have to put the value in the expected column. So this is 800 means p square. This is 185 means 2pq, and this is 15 means only q square. These are the observed values. Now we have to put the expected values. So here 796.5, that means how we calculate, we have to calculate, the formula is written here. Okay, next one. And clear? So p square, q square and 2pq. P square value is first of all here 796.5. This is expected value. Q square is 11.5 and 2pq is 192. So you can see that the value is very closely related with the observed one. Okay, like that 796.5 here 800, q square is 11.5 here 15, and 2pq is 192, here is 185. Just very close to the observed values. Okay, but not appropriate exact. And it's not possible, obviously, you know that this is a random weighting, so it's not possible. But as it is very close to observed values, that means here the HW law is acting. Okay, so the values remaining always 0 to 1. Which value? P plus q value, that remain always 1, towards 1 or maybe 0 to 1. Clear? So this is the actual derivation of Hardy-Weinberg law. That means how you can calculate the allelic frequency from the genotypic frequency, or the genotypic frequency from the allelic frequency. That means you can get that the observed, if you have the observed values, you will get that expected values related to the genotypic frequencies. Clear? So this is the second part of the Hardy-Weinberg law. Another part also remaining. So we, in this video, it's not possible to explain all the thing about this law. So you have to follow this channel for getting the next part of the Hardy-Weinberg law. Okay. So thank you, and again I say to you, all of you, thank you for subscription, for supporting my channel or your subscription. Thank you.